All right, so what I'm going to do, we didn't get to this in section 2.2. I'm going to look at it on Monday. But just in case you want to get ahead on the homework, I just want to do this last part of section 2.2. So, you know, if you want to finish that section over the weekend, you can. And then again, I'm going to be going over this on Monday. So the last two things to mention in this section, one is the sandwich theorem. So the sandwich theorem is this. Now let's say we have some x value c, and c is located on some open interval on the x-axis. So let's say we have this. We have an interval I, which is from A to B. So that means on the x-axis, let's say this is our x-axis. Here's A, here's B, and somewhere in here, we've got some number C. Now suppose on this interval, for every x in this interval, so every x value in that interval I, we have this. There's a function g of x that's less than or equal to a function f of x, which is less than or equal to a function h of x. So there is one caveat, though, I do want to mention. It is possible this might not hold at the point C. Now, I'm going to treat this really as a detail. So I'll address this later. But let's say we have this. This is what's going on, except possibly at C. But if it's not necessary for this first part to picture what's going on. And I'll address what happens if this doesn't hold at C in a bit. But let's say this is what we've got. You choose any x in this interval, and if you want for now, if you choose C also, just for now. This is holding. Say that's the case. Well then, the following is true. If the limit as x goes to C is g of x equals the limit as x goes to C of h of x is equal to L. So in other words, g of x and h of x, they have the same limit at x near C. As you get closer to C, g of x and h of x appear to be heading towards the same y value. If this is the case, and f of x is between these two functions, then the limit as x goes to C of f of x is also going to be L. Now, of course, we're assuming the limits exist. So that means after we've taken our expression, we've reduced it, we've tried some algebra tricks with it, and then we take the limit, and the limit actually we do get a number when we take our limit. So that being the case, if f of x is between these functions on that interval, well then if these functions have a limit L when x is near C, well f of x will have a limit of L if x is near C. So let me draw a picture. And again, for now, let's not worry about that inequality not existing at C. We'll address that later. So let's see, let's say we have this. And let's say we have something like this. say this is g of x. And then we have, say, something like this. Let's say that's h of x. And then what's between these two functions, this is f of x. So f of x is between g of x and h of x. And anywhere on this interval, let's say this is the case. Well, then as we get near c, if h of x has this limit near c and g of x has this limit near c, well, since f of x is between them, it's also going to have that limit near c. So that's the idea. And that's it. Now, let me address that one thing where we have where they say that, well, suppose that inequality doesn't hold at C. Like, what does that look like? So let's take a look at this inequality not holding at x equals c. Well, truth be told, there's probably infinitely many, oh, there is infinitely different ways it could not work at c. And I'll show you one. So this is the picture we had before. So I'm going to change this picture. I'm going to put a hole here. And then what I'm going to do, I'm going to make f of x sort of a piecewise function is what we're going to do. So this is f of x, and this is f of c. Likewise, let's take a point here. Let's call this h of c. And then we say g of c doesn't exist. Here's g of x. Here's h of x. But at c, h of c suddenly drops down here. F of c suddenly up here, and g of c just doesn't exist. Well, as far as limits are concerned, nothing's changed. Remember, the limit says as we're very close to c, it's not the same as saying we're at c. So the limit of g of x, as x goes to c, well, if you're very close to c, you're going to be up here at this limit. For h of x, if you're very close to c, well, you're going to be here at this limit. Same for f of x. F of x, if you're very close to c, you're going to be up here at this limit. So since we're never equal to c, it looks like all these functions, as you get closer to c, your y value is going to be very close to L. And it's only when you're at c is when things go haywire. But we don't worry about that. So that's one example of what they're talking about. So something that you don't need to worry about, what the value of the functions are at c. We're just looking at the value of the functions when they're near C. So let me do an example. So let's say we have this. So when x is near 0, we have this inequality. So we want to find the limit as x gets close to 0 of x sine x over 2 minus 2 cosine x. All right. So what we can do is this. Let's take g of x to be 1 minus x squared over 6. Well, then the limit as x goes to 0 of 1 minus x squared over 6 will be 1 minus 0 squared over 6, or 1 minus 0, or 1. So as we get close to 0, g of x gets close to 1. Now let's let h of x be the constant function 1. So the limit as x goes to 0 of something that always has a y value of 1, well, that's just going to be 1. So this is what we've got. So what this says the limit of g of x, so x goes to 0, of g of x equals 1. The limit as x goes to 0 of h of x equals 1. And then we have g of x less than or equal to f of x less than or equal to h of x. I mean, that's a hard inequality, but even if it was a softer inequality, it would still be okay. So what this says by the sandwich theorem the limit of f of x as x goes to 0, which is the limit as x goes to 0 of x sine x over 2 minus 2 cosine of x, that's going to be equal to 1. So that's the idea of the sandwich theorem. And it's interesting with this one. I mean, initially, if you look at this, if you were to try to take the limit of this function, well, what you're going to get, you would substitute a 0 into x, because we're going to say, well, it's practically 0. We can try this approach. Cosine of 0 would be 1. 1 times 2 is 2. So you're going to get 2 minus 2 is 0. Ooh, we got a 0 on the bottom. So, and then 0, sine of 0 is 0. So we're going to get 0 divided by 0. So it doesn't look like it's going to work. But of course, remember, this isn't algebra. This is calculus. We're dealing with limits. X is close to 0. It's not equal to 0. So is there any way we can, I don't know, simplify this somehow? Let's see. I don't know, that's kind of tricky. So we'll save this for another time. And there's another way you could go about this, but I'll talk about that some other time. If you run into the situation though, where you're having trouble coming up with this limit, if you know this function is between two others, then you might be able to use your sandwich theorem to come up with this limit. Now you got to be a little careful with this. What the sandwich theorem sometimes can do is it'll give you an idea of, well, the key thing about the sandwich theorem is that you've got to have your limit for g of x equal your limit for h of x. This is actually really important, and here's why. If this isn't true, let's say this is h of x, and this is g of x. Well, this would be the limit for h of x. I'll call this L sub h. This would be the limit for g of x. Let's call this L sub g. And this is x is 0. So let's say we have c is equal to 0. If the limits of these two aren't equal, but f of x is still between, well, just knowing these two limits won't tell us what the limit of f of x is. So this is required. So if they're not equal, we won't know exactly the limit for f of x. Write this up here. So that's just something to keep in mind. You do need this condition to hold, otherwise you could get something like this. And we still don't really know where f of x's limit is. Now, this isn't for nothing. I mean, this does tell you whatever the limit of f of x is, it's not above this value and it's not below this value. So that does count for something. But you need these two limits to be equal to each other to find the limit of f of x, the function between these two functions. All right. So the last thing to mention in this section is what I'd call the inequality theorem. And it basically works like this. So if f of x is less than or equal to g of x, again, on some open interval like we saw before, then, well, we'll see this. And again, this holds, or back up and say this differently, the limit inequality is still true, even if this inequality doesn't hold at x equals c. It's the same thing that came up with the sandwich theorem. Same idea. So just sort of a little note. All right. So the one thing they mentioned in the text, I want to show you an example, and the one I'm going to use, let's see here. Let's let g of x equal the absolute value of x, and f of x equal to 1 minus the cosine of x. Let me see something here. Let me double check that one. Yeah, 1 minus cosine. All right. So if we graph this, here's our f of x. So I'm using the same example in the text. This is example, let's see, it's a note at the bottom of page 65. But near 0, we actually have a hard inequality. We have f of x less than g of x. But actually, at 0, these two are equal. So the moral of the story is this. Even though g of x is bigger than f of x everywhere away from 0, at 0, they're going to be equal, and they're going to have the same limit. So the warning in the text is that if you look at the functions, the way the inequality is set up, where f of x is less than or equal to g of x, you could actually make that stronger in this example. You could say f of x is always less than g of x, or you could say something like this. So even though, for this example, So even though f of x is less than g of x, oh, and let me put this in here, the limit is equal to 0. So even though f of x is less than g of x, everywhere near 0, we still get that the limits turned out to be equal. For this particular example. Now, it's always safer to say less than or equal to, so I'm just going to do that, because it is possible some functions, when you compare them, f of x's limit will still be less than g of x's limit. That can happen. But it is possible they could be equal. So that's just something, a little note in the textbook we wanted to point out. So that's it. Again, this is just if you want to finish up section 2.2. I'll do this again. I'll visit this on Monday. But other than that, just wanted to have that available to you for the weekend. And other than that, have a wonderful weekend.